So Herbert Spohn from Technical University in Munich, Germany, is a statistical physicist and a mathematical physicist. He works in the area of non-equilibrium statistical physics, in particular on kinetic theory, hydrodynamic theory, and dynamics of stochastic particle systems and growth processes. He has made important contributions in understanding of the Kardar-Parisi-Zhang equation for surface growth. His interests also include open quantum systems and non-relativistic QED. So he's recently his work on fluctuating hydrodynamics has led to new results on universal long-time behavior of correlation functions in equilibrium correlation functions in large class of systems. He has written two books called Large-Scale Dynamics of Interacting Particles and Dynamics of Charged Particles and their Radiation Field. Herbert has been awarded a number of awards, just name a few, the Danny Heinemann Prize for Mathematical Physics and the Leonard Eisenberg Prize for Mathematics and Physics. This year he got the Max Planck medal, which is the highest prize in physics in Germany. So Herbert will be here for this week and the next week, and he's giving another talk next week on Monday on basically this hydrodynamics of nonlinear Schrodinger equation. So today he's talking on Landau-lifshitz equations of radiative friction.
So thank you very much, Abhishek, for this kind introduction. It's a pleasure to be here. I was here sort of like a little bit over a year ago and was extremely impressed. I mean, at that time there was sort of still a lot of construction going on, but now it seems that the construction people have disappeared and they have been replaced by gardeners. So now they make flowers and trees and it looks very nice. So I'm really amazed how much progress we made over 1 year. Then I would like to thank the organizers of this fundamental problems workshop to be able to sort of, that you participate and be able to sort of talk, listen sort of to that talk. And the topic is, I want already, I mean, I think it's fundamental. I mean, so in that sense, maybe it does fit into the workshop, but it's also h bar equal to 0. So you will see, and I hope you sort of enjoy what I'm trying to tell you. So let me sort of first put a little bit the setting. I mean, so I guess most of them I will use the transparencies, but I mean, this starting point, I mean, is sort of maybe should be a little slow, and then so everybody can follow what I'm trying to say. So imagine that you have, so the setting is a charged particle. Of course, there could be many, but let's assume that we have a single charge. It sort of moves on a trajectory. I mean, so this is maybe Q of t, and well, maybe you have a momentum. I mean, so this is our charged particle. Okay, and now this charged particle is coupled to the radiation field. And the radiation field is slightly more difficult to draw. I mean, so imagine that there's some intensity over here, maybe. Okay, and I don't know. Okay, so that's the problem which we are looking at. And of course, you know this extremely well. I mean, that's sort of which you learn in your, I don't know, basic courses in theoretical physics. And there are two sort of borderline cases which are trivial, but let me just repeat them. So one of them is that you imagine that you prescribe the Maxwell field. So these are then particular time-dependent fields. Now out of this you can construct the Lorentz force, and then you just solve the equations of motion given that Lorentz force. And so from this you compute the trajectory of the particle. But there's no back reaction of the particle to the field. I mean, the fields are simply given. Okay? So that's problem number one, which you can do. And problem number two, which you can do, is sort of, in some sense, the converse problem. I mean, you imagine that somehow prescribes the trajectory of these particles. So there's a given sort of trajectory Q of t. And then you look at the solution of your Maxwell equations with that particular inhomogeneity. And then you get this Linard-Wiechert potentials anyway. So that's a problem which you can also solve. But of course, again, I mean, you know, there's no back reaction of the field onto the particle. I mean, the particle is just given. And now it looks a little bit sort of strange. I mean, that we are just looking at these limiting cases. And so you would think it would be of great importance. And they are useful to actually really consider the truly coupled system. I mean, the system which consists of a point particle and of the electromagnetic field. Okay? Now, why is this? Now, you would think that this problem has been solved many years ago. Well, to some extent, of course, yes, but I mean, I will tell a little bit about the history later on, but the first thing which one should understand is, I mean, what kind of new physical effects appear if we really look at the truly coupled system. Well, there are actually two things which come up more or less directly. I mean, the first point is that the energy-momentum relation of this particle will be changed. So imagine that it was a non-relativistic particle, and so I have an energy equal to 1/2 p squared maybe. And, but this energy-momentum relation will be changed because, you know, as the particle moves, it has to drag along the Maxwell field, which also carries some energy. And therefore, you know, the way how the particle responds to external forces will not be the one, will be different from the one if I just imagine that the particle is moving by itself, not coupled to the field. So that's number one. And number two is also sort of well known, namely, as the particle moves and you sort of compute these trajectories and you look at the energy balance, then you see whenever the particle is has a non-zero acceleration, it will actually radiate energy. I mean, that's sort of indicated up here in this picture. It will actually radiate energy to infinity. And so the idea that I have an energy-conserving dynamics for this particle, I mean, this was sort of the one where I just solved the equations of motion with the Lorentz force, which of course is energy-conserving, doesn't make any sense. And so it's clear that if I want to have sort of the actual motion of the trajectory, I cannot just describe this in terms of some Hamiltonian, but I have to add friction terms. And that's sort of what is in the title. I mean, radiative friction just tells you it's a friction which comes about because I couple the particle to the radiation field. Now, problem solved. I mean, I don't really have to say very much more. Why is it fundamental? Well, the reason why it's fundamental is that you sort of write down the two equations, which later on will come in some version, but just write down the two equations, and well, you look at them, you stare them for a while, and then you realize that that the equation of motion for the particle, I mean, these are point particles, this point particle at the moment, doesn't make any sense whatsoever. Why? Because, you know, as you solve the Maxwell's equation, you put in this Lienert-Wiechert potentials into the Lorentz force equation, then you realize that exactly at the position of the particle, these objects are diverging. The potentials have a Coulomb-like singularity. And so when you ask to evaluate the force on the particle, you will get sort of a meaningless expression. And it's really meaningless. I mean, you know, of course you can now think, well, maybe you can discretize all kinds of things, but you know, as written, it just doesn't make any sense. And so this is why it's called so sort of fundamental, because, you know, the first naive guess, I mean, doesn't work, and now you maybe have to worry. I mean, you know, does this particle have an internal structure? Where does it come from? I mean, what are really the true equations of motion? I mean, what is their behavior? How does the friction appear? All these kind of things sort of become a little bit shaky because the fundamental equation sort of, the first naive fundamental equation which you write down is sort of undefined. Okay? All right, so now let's see what the setting is. I mean, so I'm just repeating in a few words what I said already, but to make sure, I mean, so first of all, we are looking at a charged particle. I mean, so you might want to think of an electron, which is, but you know, in principle, any charged particle will be okay. It will be small in size. I mean, so this has to be quantified later on, but you know, I'm not thinking of a macroscopic body. I'm thinking of something like an electron, let's say, or other elementary particle, has mass m, position, momentum. Then there are two parts of the Maxwell field. So one of them is the dynamic one. Dynamic just means that it will be parts of the equations of motion. So we will have to solve some equations of motion to determine the dynamic part of the Maxwell field. And then there will be also external fields which are simply prescribed. I mean, so they are, could be time dependent, time independent, but they are given. They are not part of the dynamical problem. Okay? So the degrees of freedom which we have to look at are the position momentum of the particle and then all the degrees of freedom of the Maxwell field. Okay? We do this at h bar equal to 0. If I take h bar strictly positive, then we are really on the level of QED, which is sort of I'm certainly not an expert on, and you know, won't say a single word on it, but of course, then it's also sort of a very important physical problem. But I mean, for me, h bar is equal to 0. And you just should remember that, you know, if you, for instance, look at plasma physics, I mean, you know, they're very happy to put h bar equal to 0, right? I mean, there are many problems of this type in nature where I can ignore quantum effects. Of course, eventually they will be important, but for most purposes, they are not. Okay, so I'm in this regime. I look also at temperature 0. I mean, that's another restriction. You can think that sort of whatever, you know, sort of background radiation, and then sort of the Maxwell field is at some particular temperature. Then, of course, things become very different, and so again, I'm not going to say anything. I will be always at 0 temperature. Now, the first sort of very qualitative information which you will see coming up throughout the talk is that the friction, in a certain sense, is much, much smaller than the effective Hamiltonian. I mean, what I mean is that, you know, if the motion of the particle is sort of more or less on a circle, you know, it will be modified, that circular motion will be modified only very, very little by the friction. You can circle your million and million times and you will hardly see any effect of the friction. That's good news because, you know, I mean, as I move my hand, I'm moving charges in an accelerated way. If this would sort of produce some friction, I mean, life would be terrible and presumably all of us wouldn't exist, right? I mean, the fact that it's small is actually sort of, I mean, it's also maybe a problem, but to some extent it's actually sort of quite convenient. Okay? If we would constantly feel radiative friction, I mean, that's not such a good idea. Okay, now, let's see a little bit. Okay, so I guess Abhishek mentioned already the book. I mean, I should say that, you know, I haven't been working on this topic for quite some time. And so it's actually a pleasure. Maybe it's good for you. I don't remember all the details so precisely, and so, you know, it will become sort of more understandable, I hope. Okay, so this is sort of, you know, was sort of finally put into the book. I just want to mention two which I thought sort of are nice original work. I mean, there's one rather extensive study with Markus Kunze. I mean, there we studied the problem for these charges when they're actually moving compared, when they have a velocity which is small compared to the speed of light. So this is the electromagnetic double star pulsar problem. And it's an amazing problem. I mean, you know, when you, of course, the real problem is the one in general relativity where people sort of do extremely complicated and tricky computations. And we wanted to understand in that much, you know, in the simplified version, we want to understand what's going on. And the simplification is that the Maxwell field is governed by linear equations, whereas if you look at the gravitational fields, I mean, these are nonlinear equations, so much more complicated. Okay, so then there's other work which is sort of extending until now, where we mostly studied the case of zero external field and sort of asymptotic properties like scattering theory and things like this. So, but I'm not going to say anything about, you know, I just want to give you the general picture. Okay? I mean, some of the things which I tell you are actually, there's some chapters in the book which sort of explain these things in more detail maybe. And if you really want to look up, I mean, then the good place is to look. Okay, now there's another reason why it's fundamental. I mean, this is sort of a more recent sort of development. People are building this what they call the ultra-strong laser sources. I mean, there are several of these sources which are built in Europe. And of course, you know, there's sort of a lot of material science applications, why they want to build such extremely strong lasers, presumably also military applications and others. But, you know, when they write these proposals, I mean, they also want to put one fundamental physics problem. And when you look up their proposals and then you see number one, it's exactly the issue of what is, in a quantitative way, the description of radiative friction. And they're still working on it and they're still hoping to see it. And then as I talk, can you explain you a little bit more why it's not so easy to see, but I would like to explain you what is the basic principle, you know, what they're trying to do. So, as I said, I mean, the friction is, radiative friction is a very, very small effect. And so somehow in order to do this, you have to do something sort of, I mean, you have to do some extreme action. And what they propose basically is the following situation. I mean, you have sort of, you know, maybe a bound electron sitting here. I mean, this is my electron, or sort of maybe bound to some substrate, I mean, in some condensed material also. I mean, so anyway, think of this electron essentially at rest. And now you take an extremely, extremely strong laser pulse. I mean, laser pulses which you still have to build, you know, the corresponding machine, or maybe now they believe that they have sort of already sufficiently strong intensity to do that. and you simply hit that electron. Okay? Now, but the electron, so the laser pulse, of course, has a finite extension, so the laser pulse will just pass by the electron, and then after it has passed, I mean, then the electron is just sort of basically moving without any external forces anymore, right? And so a typical trajectory of this particle, sort of, very schematic, is that there's this huge acceleration, so, it really oscillates extremely fast. It's a very high acceleration. Not too many oscillations because, this is going with the speed of light, so maybe 10 or 8 or so. And of course, as it does this motion, it will radiate energy, or radiation, right? Okay. Now you do two things. I mean, so first of all, you very carefully measure what is the radiated field. Okay. And now you do a theoretical computation. The first theoretical computation is that you look at this situation and you regard the laser pulse as an external field. So you just solve the external field problem. Okay. That gives you a particular trajectory. And on the basis of this trajectory, just as I explained to you, you can then work out what is the emitted light. Okay. Now you take that result and you compare it again with the theoretical computation. And for this, I mean, this is why I put the title. For this, you really have to know, what is the correct equation of motion, including radiative friction. So you add the radiative friction, and now on this means that the trajectory is just changed a little bit, but the transmitted sort of the light which is emitted is of course now changed. And now they look at the experiment and they see whether from this difference they can actually sort of conclude back that they have used the correct equations of motion for the friction. Okay, so that's the basic principle. Maybe if I have time, I will show sort of my proposal, which unfortunately nobody picked up, but this one is sort of something which is happening and is going to happen in the next years. Okay? I mean, what the result will be, I mean, we don't know. And there's a lot of technology going into improving on this very simple-minded situation and sort of making, the acceleration even more than what you expect by, anyway, so that's a story by itself, so I will not go into it. I mean, it's just sort of with this basic idea. Okay, now let's see. So let's go a little bit to the history of this problem. I mean, this clearly, it's end of the 19th century, basically, where these things came up. And the person who sort of wrote like three or I think 3 long volumes on this problem was he said, well, okay, I mean, of course he realized, I mean, maybe not, that was not the words he was using, but he realized that you cannot take point charges, so he just postulated some charge distribution. So, and short distance cutoff in your equation, but physically you can really think that the charge is sort of a little bit distributed, and at that point he had various models, but he just used it a completely rigid charge distribution, and then he started to compute what are the equations of motion. And the result which he found is actually quite remarkable. I've written these things now in a relativistic notation because it's short, so these are all, the X are really world lines here, but it's just sort of to make the formula sort of slightly more complex. So what he found was what I said already, namely he found, first of all, that the inertial term, I mean, the energy-momentum relation will be changed. Here I put just the mass. That's actually not true. It's a more complicated energy-momentum relation. And of course, he realized that depending which kind of model he would make, he would find sort of different type of energy-momentum relation. That was a problem because, I mean, nobody knew what the charge distribution of an electron would be, and now you get an energy-momentum relation which does depend on the particular assumption on the charge distribution. Now, this part of the story was finished in 1905 because Einstein said, look, I mean, there is no choice. I mean, there's the principle of relativity, and that fixes for you, whatever you do, fixes for you what this inertial term should be, right? I mean, so in some sense, this model dependence was resolved in a totally unexpected way. I mean, it was not resolved by saying, this is the true charge distribution. It was solved by saying, we must have equations of motion which are relativistically invariant. However, the second part is sort of has a different story. So these are just the external forces. The second part has a very different story. I mean, you look at this thing, and what you discover is that this one is completely universal. I mean, in the sense that the only thing which enters is actually the total charge. The particular distribution of the charge, I mean, the particular way how you do the cutoff, I mean, just doesn't play any role. And Abraham, of course, he couldn't know. His formulas look very lengthy, But then von Laue, a few years later, sort of realized that actually this friction term can be written in a relativistically invariant way. All right? So this was sort of the status. And then there's actually an interesting book, which is 1906 from somebody called Scott, who sort of summarizes many of these things. I mean, of course, many of this part has been sort of channeled into what you read in textbooks on electromagnetism. But he also discusses somewhat this friction term, and he makes some very simple conclusion. He simply says it's so small that further on I will disregard. Okay, it's just really a very small term. Okay, so you might say that, well, I mean, our grandfathers have solved the problem, and here are the equations of motion, and so we just go ahead and do whatever computation we do. I mean, strong laser pulse, and then we look at the equation of motion. Okay? We look how this moves if I add this friction term to this. Okay, so now there was a question. Oh, okay, so now we think a few latest quantum theory. Then move to QED, and then Dirac sort of somehow, because of QED, he started to become interested in this topic again, right? I mean, so before there was maybe no particular reason, but QED wants to do exactly this. I mean, he wants to quantize the Maxwell field and the particle or the particle field, and then sort of look at the coupled system. Okay? And so he looked at this equation and he said, look, I mean, this is a completely ridiculous equation, because I have this derivative up here, and if you just solve this equation, you will see that you have exponentially diverging solutions. So, I mean, nobody apparently made this observation before. Okay, so what to do? Well, I mean, the computation is correct. I mean, there was no error in the algebra, but the resulting equation is absolutely meaningless. So Dirac said, well, I mean, sort of, world is not so unfriendly to us, and then somehow there must be some truth to it. And what he then simply postulated is that the physical solutions are singled out by this asymptotic condition. So he wants to look at solutions of this equation which satisfy that the acceleration, the limit as c goes to infinity, vanishes. Well, okay, there are two parts to this story. I mean, one thing you might believe, of course, it's a little bit unsatisfactory after you have done a careful computation, that you put some extra condition which comes sort of out of nowhere. I mean, why would I put suddenly some boundary condition at infinity? I mean, that sort of doesn't look like, I mean, too convincing. The other thing is a more practical question. How are you going to deal with this thing? You see, I mean, you have all these many solutions, and now you're supposed to single out sort of a very small subset which satisfies this condition. I mean, how are you going to do this in the practical sense? Imagine that I want to solve this laser problem. I mean, and you have these quick oscillations. I mean, how am I going to figure out which solution satisfies this asymptotic condition? So it's not only that maybe you're a little slightly unsatisfied from a sort of more basic physical point of view, but you're also dissatisfied from a practical point of view. I mean, how I'm going to implement that particular boundary condition. All right, so that's sort of certainly unsatisfactory. Now I want to first tell you how one actually properly deals, to my taste, properly deals with the Dirac asymptotic condition. Okay? So I'm not, at the moment, I'm just sort of simply assuming that what was written up here sort of, I mean, there's some level of truth in it, and I'm trying to find out a little bit more precisely what is actually the truth, right? And then in the second part of the talk, I will, in the second part of the talk, I will come back a little bit more to the question of, well, what do we do with the coupled field? Okay, so what to do? Well, you see, okay, maybe I should go back. I always emphasize that this term is very small. Now, you see, you have here just a differential equation where the highest derivative has a small prefactor. And that's a problem which somehow these people in electromagnetism never understood. I mean, I gave many talks, and it's sort of a point which is difficult to grasp, to get across. But there's a very well sort of developed mathematical theory which is called sort of singular perturbation theory, which deal exactly with differential equations of that type. So I have sort of an ordinary differential equation, but the highest derivative has a small prefactor. And the question is, what is the solution? What is the solution structure of that equation? And so in order to explain to you, I want to sort of use a very simple example of that type. And I simply claim that exactly the same theory will actually also apply to this equation. I mean, what is called the Abraham-Lorenz-Dirac equation, sometimes. I mean, so. No, Abraham-Lorenz-Dirac equation, that's how it's called. Okay, so let me try to give you the simple example. So here, it's just a model example. So I have x and y, which are two real variables, and then so I have first order differential equation. And sort of the y is sort of the higher derivative, and I simply put an epsilon in front of this. Right? And you want to understand the solutions, so it's a two-dimensional phase space, and you want to understand the solution space of that phase, of these equations, okay? Now, okay, so now maybe you would think sort of to do sort of like a naive perturbation theory in epsilon. That's somehow what I'm going to do, but I want to explain you a little bit what the structure is behind it and why you can sort of, if you use it the right quantity, why you can actually do perturbations here. So first of all, I mean, let's put simply y equal to 0. Well, I mean, then you get simply, you know, this type of constraint, and the solution, you know, solving this equation sort of gives you sort of, you know, somehow the motion to lowest order, right? I mean, there's a complete constraint over here. This is, so you put the constraint into this equation, and now you have sort of, I mean, this corresponds to the Hamiltonian equation later on. I mean, now you simply have to solve, you know, there's an absolutely perfect constraint, and you plug it in, I mean, then you get a closed first order equation for f. You don't need any initial condition for y because, you know, it's squeezed immediately to that value, and therefore sort of that's it, okay? All right, so that's the first order. But now, of course, we are interested sort of in higher orders. And now, when you sort of just fix this value and then you look at this equation, then you see that this one is sort of an exponential solution, but, you know, it goes with 1 over epsilon. So for a very small epsilon, it will diverge extremely, extremely fast, right? I mean, so that's the runaway solution for that system. Yeah. But now there is sort of a theorem that, you know, what I saw to lowest order is somehow not completely lost. And the assertion is the following. So now I'm fixing epsilon but small. And then the assertion is that you know, this constraint manifold, I mean, that y has to be equal to this function h, is now simply slightly deformed. So it's important to realize this geometrical object because, you know, in the equation of motion, things look very singular. If I sort of, you know, if I, okay, so it's important. This is sort of the important object. So the claim is that it's formed, I mean, of course, it depends on epsilon, to a slightly deformed manifold, I mean, sort of, which is given by a new function, which is h of epsilon. So that's an abstract theorem which assures you that, you know, if there are some regularity assumptions on f and h, I mean, there will be this h epsilon. And this is sort of, locally it's okay, and it's a smooth function in this parameter epsilon. Of course, you know, the whole manifold, C epsilon can be very complicated. It can fold over, and it cannot be really described by a function anymore, etc. But that's sort of a different issue. I mean, for small epsilon, you can think of this just really like a nice function. Okay? Well, and now it's clear the way how we should do it. You see, if I take this constraint and if I put it back into my equation, then I get a closed equation on this line which is defined by, or this manifold which is defined by C epsilon. I get a simple evolution equation, right? I just plug this in over here, and of course I have to know the right h epsilon. Now, if I want to do an expansion, because usually I don't really know this h epsilon very precisely, then, well, all what I have to do is I sort of have to look at the equation which defines this one. I have to do an expansion of h epsilon, which I can do, which is locally smooth, and then I get sort of a well-defined equation of motion up here with no runaway solution. So maybe that's a little bit obscure what I was trying to say, but I put a picture, then you can sort of see this more clearly. Sorry, this has to go this way. Okay, so here. Well, it's part of the theory that there is such an h epsilon, right? I mean, so if you look more deeply, I mean, you find sort of a fixed point equation for that function and so on. Okay, so here I draw you this picture, but you should think of this evolution. I mean, so here was my original C0, which is completely constrained, but now as I turn on the epsilon a little bit, then this will be deformed, and the assertion is that so, you know, this is a line in a two-dimensional space. So if I just take an arbitrary initial condition, I will simply have a runaway solution, which runaways very quickly to infinity. But if I'm sitting exactly on the line, I will have a slow motion. So that's the fast motion. I have a slow motion, And the slow motion is governed by a first-order differential equation. Okay? And now I do this expansion. I mean, now you have to sort of plug in this formula. I mean, it's not very important to see the details. I just want to emphasize that as I turn on an epsilon, there will be a first-order equation, which is sort of just given by the constraint, and then there will be a second order, which sort of in our case would be a friction-like term. I mean, friction is now sort of a physical term. It's just the first-order correction to this. Okay? And now what I'm trying to say is that if you really want to get the appropriate physical solutions out of this formal computation, what you have to do is you actually have to constrain the solution to what people call the center manifold, to this particular deformed curve. Okay? So it's just exactly the same theory which applies, and what you do is you simply insert this, and what you find is then the following equation. Now it's a second order equation. You know, it's just like in this case that, you know, I'm always working here with first order equation. In our case, things are second order, and what you find is, of course, you know, this Hamiltonian term, which is fine. And then you can find a friction term, which is now sort of slightly more complicated. There's a dot missing over here, and you have sort of the small factor in front, and you have this particular combination of terms, which presumably, you know, doesn't tell you anything. I will make an example at the moment, but this is now a bona fide second order equation, no runaway solutions whatsoever. So it's that equation which I propose is sort of the correct equation for radiative friction. Now, you know, after I've worked on this and sort of figured out this singular perturbation theory, then I talked to experts, and they mentioned that, well, you know, there's Landau-lifshitz, and you know, there's something very similar. In fact, I mean, as you go to Landau-lifshitz, which I should have done before, but in any case, I mean, you find, starting from 1915, all additions, you find sort of this equation, maybe in, I think even in the relativistic version, you find this equation, but what Landau-lifshitz doesn't explain is sort of this geometric picture up here. I mean, you know, they sort of basically say, well, look, I mean, we take this as a first order, and then we resubstitute and substitute again, and then we get a sort of this equation. Now, this substitution will sort of look, to some extent, sort of somewhat arbitrary. But if you understand that, you know, what is behind is this singular perturbation theory, you know, they are exactly the right steps. Okay? So in some sense, you might say that you know, it's sort of an underpinning of what Landau-lifshitz proposed before, and in the field, I mean, you know, there are many Landau-lifshitz equations, but this particular equation is called the Landau-lifshitz equation of radiative friction. All right. So now let me give you two examples. I mean, so that you can see that it's sort of a little bit, you know, it's rich, more rich than what you know from ordinary friction. I mean, so here let me just sort of take the previous example. Particles in one dimension sitting one dimension and sitting in an external force field, no magnetic field. And then what you find is that of course here you have the usual force, but this is now the friction term. It's the derivative of the potential multiplied by the velocity. Okay? And you see that the friction doesn't have a definite sign. So if I take here my harmonic oscillator, then of course this has a definite sign, and then it will just oscillate and will sort of lose energy, will end up at the minimum. But now let's take something like a cosine potential. Then you see that down here it will be slowed down because you know, this has now a positive sign. It's the minus, then will be a real friction. But up here it will be actually anti-friction. And so as the particle moves, at the top it will be accelerated, and at the bottom it will be sort of decelerated. And this will go on for a while, but you can check that after a while, I mean, it will lose so much energy that at some point, you know, it's in energy drops down and is then bound by a well. And then once it has found that particular well, it will just oscillate and will come to rest. So these equations, despite the fact that the friction has no definite sign, eventually, you know, the system will go to some final rest position. So, and now it depends, of course, a little bit on the precise forces which I'm putting, but you know, it has sort of this property which we sort of think of friction. I mean, you know, as I put friction, then eventually things come to rest. Now here, you know, I mean, come to rest, it's not the correct notion. Depends on the external potentials, but in any way, I mean, so the thing which I want to emphasize that you can have both signs, but eventually sort of the friction part of that term somehow is dominating and eventually sort of comes to rest. Okay, so there's another nice example, which maybe because of time I'm not going to go into, which is the panning trap. Actually, it's a panning trap which I propose as a possible experimental test for checking whether the Landau-lifshitz equations are really the correct equations of radiative friction. And the idea of the panning trap is actually very different from what people usually do with the hard hitting. The idea of the panning trap is that it's a very small effect, but if you do it sufficiently long, then eventually it will add up. Okay? And the panning trap is actually a beautiful example. I mean, I have some data on the panning trap. I mean, people use this, you know, the panning trap was developed in order to measure the G-factor of the electron. They were not interested in radiative friction, but they give you data of what this friction actually is. I mean, how, for instance, you know, how long does it take for the electron to sort of reach sort of like well, okay, it's getting too complicated. So let me just point out that the panning trap is a very special example that you have sort of like it's a harmonic potential I mean, usual harmonic potential in the 3 direction, but it's sort of inverted harmonic potential in the 2 other directions. It is stabilized by an external mechanic. You can look it up. I mean, I think it's really an interesting example, and I believe if people could revitalize, I mean, these panning traps for that particular purpose, in particular, if you make the magnetic field, they always do the magnetic field in the Z direction because that sort of gives them the nicest orbits where they can measure the G-factor. But if you want to test the theory, I mean, then you should actually tilt it, and I mean, you see all kind of interesting effects. One can do it. One can look at ultra-relativistic corrections. I mean, then anyway. Okay, so this is sort of the end of part 1. I mean, so what I tried to explain you that you know, there's this funny equation which has runaway solution, but the natural sort of prescription is to use singular perturbation theory, and then you get sort of a nice equation of radiative friction. It's second order. You can put it on a computer, and you know, the experiment. What people want to do with these ultra-strong laser pulses, when they compute this emitted radiation, including friction, they would sort of always use the Landau-lifshitz equation. Yes, sure. Good. That's a very good question. Okay, so now if I fix, okay, so if I fix epsilon small, then, I mean, maybe it's not a general theorem, but at least for the cases which we sort of understand, then the asymptotic condition does single out the motion on this, I mean, on this manifold of slow motion, right? So in that sense, I mean, you might say that Dirac agrees with what you get from singular perturbation theory. However, the important point here is that, you know, then you get all kind of, you get these pre-acceleration effects, you get all kind of spurious effects. The main point is that here I can do perturbation theory in the small parameter. And then I get really sort of a sequence of just ordinary differential equations which I have to solve. People have tried to do that, I mean, but it's very complicated. You know, it's a complicated shooting procedure of how you actually sort of manage to satisfy the Dirac condition. Whereas here, it's just an initial value problem, and that's of course a big advantage. I mean, that's one of the reasons why people, you know, actually use it, because numerically it's superior to any attempt to you know, satisfying the Dirac condition. Okay, so now comes the second part of the story, namely what about the microscopic theory? Okay. So this we don't understand, you know, as well as what I just told you, and you will see that it's to some extent an unfinished story. But let me sort of just tell you what the approach is and how I differ from maybe what other people are trying to do. Okay, so let's take the case what Abraham proposed, namely I take a rigid charge distribution, which I call here phi of x. And so, you know, as I insert this rigid charge distribution, I make the model immediately non-relativistic. Okay? So here I've written down the Maxwell equation. I mean, here I have the constraint equations. I mean, no, sorry. So these are just the Maxwell equations. Here is sort of the local charge density. Here's the local current. And then you compute the Lorentz force. I mean, and then here, so here I'm now in the non-relativistic scheme. So Q is just the same Q as over there. So it's just the acceleration. There's some bare mass. And this is sort of the coupled system. So I have to solve this system combined with this one. And then, of course, there are the external fields, which I call EX and DX. Okay, so that's our dynamical problem. Now, once I introduce the charge distribution, it's well posed. I mean, it has solution. Of course, you know, it's sufficiently complicated, so we don't really know anything, not so much about the solution, but it's certainly a well posed problem. Okay, so here it is, and now let's have a look at what Dirac in his famous paper proposed. So he was sort of, I mean, like many people in this field were absolutely, well, I mean, they strongly believed in the idea that one has to take the point charge limit. And so what he did is said, well, okay, I mean, I have this figured out, and so why don't I just take my charge distribution, I scale it with R, and let the radius go to 0. This will go to a delta, right? I mean, so as I let R go to 0. Okay. So he said, well, I mean, let's just look at this equation in the limit as the radius goes to 0, and let's hope for the best. Okay. So, and what you see is nothing too surprising. I mean, you first see a modification of the charge by this fairly explicit factor here, and then there are forces. I mean, then there are external forces, and then in principle there are also friction forces. But what I'm trying to say now, I mean, the friction forces actually are of no importance. So, well, I mean, so you do this, and then you realize that the mass is changed, and of course, as I let R go to infinity, this factor will diverge. So as I couple it to the field, and as I remove the ultraviolet cutoff, it's more and more coupled. It has to carry more and more field energy, and therefore, you know, it becomes heavier and heavier. Well, too bad, but not too bad for Dirac. He said, well, okay, this should be fixed. So why don't we just imagine that we fix this to the experimental mass? So I keep this fixed, and then I'll take the limit as R goes to 0. This, of course, means that the bare mass has to go to minus infinity, right? Because if I want to keep this equal to 1 and this diverges to plus infinity, this better diverges to minus infinity. Now, this is a bad idea. I mean, Dirac is a great, great scientist, but I think this is not a very good idea. And the reason why it's not a good idea is that, you see, as soon as I make the mass negative, I mean, we are here in the framework of classical mechanics. As soon as I make the mass negative, you see that you know, one of your modes is simply sort of, you know, has the wrong sign, and therefore it's an unstable system. And so what you can actually prove is that as soon as you make this mass negative, then the motion is unstable, and even if I do, you know, all these nice cutoffs, I will get runaway solutions. That's actually a theorem. It's not so hard to show. I mean, it's just the point that this sort of unstable mode, you know, is coupled to all the other modes, and therefore it suffices to have in one mode the instability, and then it sort of will spread throughout the system. All right. So somehow it looked to me that going through you know, if for finite negative M0 the dynamics is unstable, I mean, maybe it's not so surprising that in the limit you will also find runaway solutions. Okay? So I somehow I mean, there's still people who sort of try to work on this idea of taking R to 0, all kind of interesting proposals. So I sort of want to take sort of a somewhat more modest sort of physical perspective, and what I want to argue that what one really should do is one should look at the situation where the external fields have a slow variation on the scale of the fixed diameter of your charge. Okay, so for an electron, I mean, this would be typical sizes, and there's also a time scale, so it should not very slowly both in space and time. And you see, if you look at these numbers, I mean, this sort of covers sort of most fields which we deal with. And so, you know, if I really violate this condition, then presumably I'm already deep in the quantum mechanical regime, and so somehow, you know, I cannot hope to have sort of a decent theory. But this sort of looks to me like a very simple sort of idea, namely that I need some external fields, and all what I require is that these external fields have a slow variation on the scale of the charge, both space and time scale. Okay. Now you say, well, look, I mean, that's the same. I mean, you know, you somehow let the values shrink to 0, and that's one limit, and then you let the fields have a slow variation. I mean, you just by v-scaling, one of them should be the same as the other one. The point is, it's not. If you really look at the coupled system carefully, and you do the v-scaling, you see that these are two different limits. Now, what is the advantage of my procedure? Well, you see, the point is that if I now take okay, so maybe I should say it like this. I mean, you know, in my formulation, I mean, the bare mass is always strictly positive. So I always have sort of a well-defined, hopefully stable dynamics. And of course, the charge distribution is completely fixed. I mean, what I'm changing, what the small parameter is now sitting in the external parameters, in the external fields, rather than in properties of the charge. I mean, the properties of the charge are sort of kept as they are. Okay? And, well, okay, so let's see. So maybe, I mean, this is sort of a little bit of almost, okay, so let me say this anyhow sort of in words. I mean, so what is the problem which you would like to do? I mean, well, I mean, now you sort of introduce, so I have this, I call epsilon this parameter of slow variation. So my external fields are sort of slowly varying in x and t. I mean, both the electric field and the magnetic field. So now I have equations of motion. Now, of course, if they're very weak, I mean, then you see that I have to see a long time in order to observe something. And so actually what I expect is that if I look at you know, with this type of external field, if I look at the position of the particle, then it will have sort of a variation of this type. I mean, it will go very far, so that's order epsilon to the -1, but then it sort of will be also slowly varying in time. And similarly for the velocities. Okay, so you see that what I have to study now are sort of what happens to in the limit of sort of, I mean, mathematically in the limit of infinitely slow variation. And what you hope and what you can show is that to lowest order in this variation parameter, you actually do find an effective Hamiltonian. So there's a formula for this momentum energy momentum relation, and then there are, you know, the forces which sort of are coming from these external fields. I mean, so this you will find to first order, but then there will be the first order correction, and the first order correction will be in fact a friction type term. And what you would hope is that you could somehow push, you know, the analysis to the level where you can show that anything else is sort of higher order. Okay? Now, so you want to approximate the true dynamics, which is this one over here. That's the full solution of your Maxwell, I mean, of the coupled system, by some effective evolution of the particle. It has two terms. It's sort of order 1 in these units, and then there will be a small order epsilon correction, which is friction-like. I put here initial slip because, you see, I also have to say something about the initial condition of my dynamic part of the Maxwell field. But I mean, so I have the external fields given, but now I have this one charge, and what do I take as initial condition for my Maxwell field? This is a problem, and this is sort of actually a very well-known problem in other fields of physics. But I like to call this sort of initial slip. I mean, so for the initial time, there's sort of a slight mismatch. And let me explain this on the next transparency, what's happening here. Oh, this is already some of that page, so let's see. Oh, okay, so I didn't put any more. Okay. So, no, I put it up here. I forgot to explain. So okay, so I fixed the initial position. So the question is on the initial condition. I put the initial condition of the particle and its velocity. So that's fine. That's just mechanics. Now, what do I do with the electromagnetic field? Now, what I do with the electromagnetic field is that I use what you might want to call adjusted local Coulomb. Now, basically, this means so imagine that the particle is at rest. I mean, then what I would do, I would simply assume that the initial Maxwell field is given by the static Coulomb field, no magnetic field. Right? But now the initial particle is not at rest. I mean, it has a certain velocity. So I have to modify a little bit the Coulomb field. I mean, this is what is called adjusted. I mean, the way how you compute this adjusted field is that you assume that your particle has been moving for an infinitely long time with a constant velocity, and then you look at the field which is sort of next to the particle. That's the adjusted Coulomb. But you see, the true motion of the particle is something different. It's not moving for an infinitely long time, sort of without any perturbation, but it's doing something else. And so these fields are sort of okay, but they're not completely okay for my particular approximate dynamics. And so at the initial time, there's something more complicated going on, but I can, after the initial step is finished, I mean, I can sort of approximate, the evolution through this effective handling process. So the way you should think about it is that I cannot take the initial condition of my particle and just put it into the effective equation. I first have to compute what is sort of the corrected initial condition which I have to put into the effective equation in order to get a good approximation to the solution. Okay, so that's maybe too many words, but let me see what next. Okay. All right, so this sort of turns out to be still sort of a rather complicated story, and in fact, what I put there as a goal, I mean, we simply have not achieved. I mean, we see friction, but we cannot, of all the possible friction terms, we cannot single out the Landau-lifshitz equation. Okay? And so somehow I felt rather unsatisfied with the situation, and so I analyzed one particular model, which I believe is very instructive. Of course, it's sort of a toy model, but I think it does capture, and I think it sort of captures, what I was sort of claiming to be true in the full coupled system. Okay, so this is an idea which goes back to Sommerfeld and Page, and in fact, there are many versions of this in the literature. So the observation is the following, that, I mean, the Maxwell equations are linear. And the Lorentz equations are also linear in the field. What is nonlinear, of course, I mean, there are nonlinear functions for the particles. So of course, it's not a linear system, right? It's nonlinear in the particle part. But the Maxwell part is sort of linear. And therefore, what people sort of automatically do, and I think it's a very reasonable thing, is that you basically can integrate over the Maxwell field and put it, because you have an explicit solution, you can put it into the equations of motion. And this gives you then a sort of memory type of equations. Unfortunately, I mean, this is very well known in other fields, but to deal with these nonlinear memory equations, which you end up with, which you can write down quite explicitly, will have a somewhat complicated structure, but then to say anything useful about this sort of memory type of equations, I mean, looks very difficult. And so what Sommerfeld already noticed a long time ago is that you can sort of somehow simplify this by, first of all, assuming that charge distribution is sitting on a sphere, and secondly, you sort of, in some sense, you linearize a little bit. I mean, so what he proposed, I mean, he didn't do very much with it, but what he proposed is that here is, so I'm using the particular case when I have a particle which is moving in plane, and you have a field which is orthogonal to the plane. I mean, so I'm using now a zero external electric field and constant magnetic field pointing in the positive z direction. And then what he proposed is that sort of this complicated memory type of equation could be replaced by this type of simple delay equation. So you see, this is the velocity of the particle at time t, and that's the velocity of the particle at time t, but sort of, the time it takes to cross the radius, I mean, minus 2r, delayed compared to that time. Right? So it's time prior to, this is a time t, and this is the time t minus 2r. Now, well, this sort of looks like a real toy model, but I think it is useful. And what you can see is that it's now a linear equation in the velocity. So you can basically sort of use spectral theory, and I'm not going into this, but all the results which I mentioned are sort of based on analyze. It's a memory equation, so it's sort of an infinite dimensional operator, but you can analyze this in great detail, and all the things which sort of I claim here, they do come out from analyzing these linear equations. Okay? And so it's clear what the motion should be without any friction. So I just have my cyclotron orbits. I'm just moving on a circle. But then the question is, what does the friction do? And let's see. So here I guess I've sort of introduced dimensional variables. So I'm looking at this equation here. I mean, there's an omega, which is the gyration frequency, and then there's sort of friction term, which is small. And here you have the delay. I mean, now the delay is by minus 12. Okay? And so I put in here numbers. Let's say, I mean, just that you see that things are not completely ridiculous. I mean, so if I have a fairly strong field, and if I adjust the velocity, that my initial radius is something like 10 centimeters, then it will just circle. It will sort of, this radiative friction, it sort of will shrink. And roughly after 1 second and 10 to the 14 revolutions, it will shrink down to 1 meter. Right? I mean, so that's a typical number. I mean, which, when you look at the padding traps, I mean, they give you similar numbers. Okay? So you know, I mean, this friction term is sort of, you know, it's not. I mean, this kind of simplification is not completely unreasonable. Right? I mean, so if I do the same computation for the full Landau-lifshitz equation, I will find sort of more or less the same numbers. Okay, so this is sort of what you have, and now let's look at these limits a little bit. Okay, so you know, you always sort of do in the Taylor expansion in the delay if you want. So this is what I've done up here, and so here you see again the runaway solution. So you know, you just did naive Taylor expansion, you get double dot. I mean, this is again the runaway solution, which clearly the original system, you know, it really shrinks. I mean, it's nothing from the runaway solution. The runaway solution just comes because you do this silly Taylor expansion. Of course, that's the first thing what you do, because I mean, you know, I mean, you cannot sort of easily imagine what else to do. But I mean, if you just end up with this particular. Well, now, but Dirac would say, you know, now we do this, and I mean, this is sort of now we let R go to 0. And 0 go to plus infinities, to minus infinity, we keep this fixed. I mean, so this term goes to 1, let's say. But then, of course, he simply ends up with this equation and with some particularly effective mass. And of course, the limit also has runaway solutions. That's what I was trying to say. So if you do the Dirac prescription with that example, what you find is that, I mean, everything is well defined, but the limit simply has runaway solutions. How do you get this submanifold of solutions which are stable? Well, I mean, you realize that if I take very particular initial conditions for my particles, so constrained initial conditions, then you can sort of ensure that you're just sitting on this sort of manifold of stable solutions. Right? So, and then the question is, you know, why in the world, where does this particular constraint on the initial condition comes from? I mean, why would somebody have adjusted initial conditions in such a way? Now, the opposite thing is what I'm proposing here. I mean, so you know, I do now a slow variation in B. I mean, it's the same Taylor expansion as before. I mean, so you see that the structure of this equation is just completely identical. Only the small factors appear at somewhat different points. I mean, so here it's just a constant, and now the small factor is sitting in front of the second derivative, where here determined the front of the second derivative was considered to be order 1, and then this one was sort of the divergent. Right? So this is now the same Taylor expansion in the new scaling leads to this particular equation. And now, of course, the claim would be that I have to look at the stable manifold, and if I do correctly the singular perturbation theory, then I end up with this equation, which of course is sort of exactly the right and nice equation. You see here the circular motion, and you see here a nice friction term, which sort of, if you solve this, sort of gives eventually the numbers which I told you. And now comes sort of the result. I mean, the result is because you can use Beckett theory. You can actually show that in my scaling, this is actually the correct limit of the true equation. So let me see whether I put this somewhere here. Yeah, okay. So now, you know, the solution map goes now over 1 time unit, so that's tau. So I have a map which gives me the solution between 0 and tau, and it maps it onto solution between tau and 2 tau, and 2 tau and 3 tau, etc. And it's that map which you can sort of, it's a linear map, but you can analyze in great detail. And what you find is that indeed you get this phenomenon of the initial slip. I mean, you know, at the initial time, I've sort of described the velocity more or less arbitrary in this interval. But then what happens is that under this sort of evolution, you can more or less forget the external field. I mean, what happens is that very quickly the internal dynamics drives to an effective velocity, which I call V bar. After a few time steps, goes exponentially fast. And it's this V bar which I have to put into the initial conditions of my equations of motion. So that's the initial slip. I mean, I cannot take the initial velocity. In fact, here, you know, there's no initial velocity. I give you the velocities over this whole interval. But I cannot just take this one. I mean, this would be sort of fairly meaningless, but the internal dynamics very quickly produces sort of the correct velocity which goes into the equations of motion. Well, and then the assertion is if I solve the effective dynamics, with that particular initial condition, and then I look at the difference between the true evolution and the approximate solution, then I get such an error term that so the error is much smaller than the one which comes from the friction, and the W evolves according to the Landau-lifshitz equation. And the error is sort of uniform in T, and then everything sort of works exactly the way how it should be. And my claim is that despite the fact that this is a toy model, if I would be able to do something similar for the full Maxwell, I mean the full Abraham model, I mean Maxwell plus Lorentz force, I would expect exactly the same structure. Okay, so now I use many words. I think I'm sort of basically finished here. So let me just sort of repeat, I mean that you didn't miss the punchline. I mean, so the punchline was that I believe that we do know what are the correct equations for radiative friction, but they become valid not in the limit of 0-point charge, but rather they become valid in the limit when the variation of the external fields are slow compared to the size of the charge. In that limit, and that's of course, when you look at concrete cases, I mean, the epsilon is something like 10 to the minus 8 or so. I mean, I'm actually very, very close to this limit. In this limit, what should be happening is that the true solution, I mean, the full microscopic solution, is actually extremely well approximated by the solution of the Landau-lifshitz equation with initial condition which you have to compute, I mean, through the initial slip. So there's some sort of initial value problem which you first have to figure out in order to sort of find out what are the correct initial conditions for the Landau-lifshitz equation. For the Sommerfeld-Page model, I mean, we have a full control. For the Abraham model, there's always something still to do, and so that's the same situation over here. They're unfortunately too weak, but I hope that at some point people will be able to support this by a little bit more stronger arguments. So thank you very much for listening.
Questions?
I'm just curious, the corresponding situation in general relativity, motion of a mass in, say, gravitational waves, does that mean, are there similar issues?
Well, I guess, I mean, this is presumably more what I was trying to say about this, this binary pulsar, right? I mean, so I think this is a situation where the velocity, well, let's say, of your particles are small compared to the speed of light, and I think that would be the same thing if I have the Mars and the Sun and things like that, right? So then I mean, then what you do is sort of somewhat a different expansion. What I'm proposing here, so I mean, the expansion parameter is the natural expansion parameter is I mean the ratio V over C, right? But then otherwise you find sort of a similar structure. I mean, you find first sort of static Coulomb potential, then you find a first order correction, which is still frictionless, but it's the first order correction to the Hamiltonian, and then that's different from relativity. To the next order, you see already the friction terms. Whereas if you do general relativity, you have to go to order higher because well, I mean, here I'm using the fact that I mean, I want to see, if I have this binary problem I mean, we have charges and we don't have gravity. So my binary system in electromagnetic theory consists of a plus charge and a minus charge. And so I get dipole forces, and therefore I get already friction sort of, at a lower order than I would get. So yeah, but this is sort of a somewhat different route because, but of course, it's the same thing. I mean, you get then in this case you get at fourth, I mean at first, second, and third order you get the friction term yeah, that's what you also, same friction term which is responsible for the pulses, being sort of slowing down and. And that's a good question. Well, implicitly, yes. I mean, it's a similar structure because it's a different parameter, but when you do the naive expansion, you also end up with an equation which it's not, okay, so there are two terms in your Hamiltonian. Once I'm still at the conservative level, then you just plainly approximate. I mean, you don't have to use any singular perturbation here. But as soon as you pick up the friction term, you will also get these singular perturbations. And the whole point of the difficulty why we don't have good error bounds is that you know, even when you try to do that, despite the fact that we have the insight from singular perturbation theory, the trouble is that you know, I mean, these exponentially diverging solutions, they somehow, you know, they're always somewhere around, and then we don't really know how to deal with them properly. In the Sommerfeld page, I mean, the nice thing is that you know, it's a linear operator, and you can easily see what the eigenvalues do, and that's something which you can always control. It's not a problem. You don't have any.
Any other questions? Well, maybe I had a question. So I can understand, like, if I take paired initial conditions, I can't use that in the Landau.
That's correct.
Right? So what do I do to get for the initial dynamics? The slip.
Well, I mean, for the slip dynamics, basically, what you do is okay. So this is on a very short time scale, and you know, as I explained, that you know, if you have slow variation of the potentials, I mean, then the forces are actually weak, right? I mean, so I'm looking at weak forces, and so for that initial slip, I can just ignore the forces completely. So basically, what I have to do is I have to solve I have to solve the initial condition, the bare initial condition for my particle together with what I call, let's say, the adjusted Coulomb potential. Okay? And now what will be happening is that if I wait a little while, I mean, then the particle will basically move with an effective, what I call v bar, I mean, with an effective v velocity. And if I wouldn't have any external forces, it just would keep going with that velocity forever. But for this, I have to solve a dynamic problem. You know, I cannot simply read it off from the initial condition of my particle. So once I have solved this problem, then I have the sort of the correct. So it just means that typically whatever I write down will have sort of a little bit of mismatch. And as the particle moves, this mismatch, I mean, the particle sort of resolves by itself, right? I mean, it does this sort of somewhat complicated back and forth between the field and the particle, and it results in a uniform motion with an effective velocity v bar, and it's that velocity which enters as initial condition in the Landau-lifshitz equation.
Okay, so I guess there are no other talks. So that was really a foundational talk, I guess. So let's thank Herbert for